Hello, welcome to today's webinar with the topic Water Reuse and Waste Minimization with Alfa Laval Zero Liquid Discharge Technology. This webinar targets those of you who want to understand the technology and process involved in zero liquid discharge. My colleague Christian Lindell will attack this interesting topic from a few angles. He will introduce you to zero liquid discharge and specifically address what are the key risks and how to manage these when designing a system. You are very welcome to ask questions in the chat box, and we will answer those in the question and answers session in the end. And by that, I leave the microphone to Christian.
Thank you very much, Magnus. And yes, welcome to you all to this webinar where we will share knowledge about zero liquid discharge, starting with the concept of ZLD and then moving more into the technical details with focus mainly on the thermal evaporation part of such systems. We really hope that this can inspire you to novel thoughts and ideas how zero liquid discharge can be applied within many different areas and industries to save water, reduce waste and transports, and help reaching a more sustainable future for us all. The starting point is that most industrial processes will use fresh water at some point, which will often result in a wastewater stream. And this is where the zero liquid discharge system comes in to treat this wastewater. The ZLD system uses a combination of technologies and process steps involving heating, separation, decanting, and evaporation to separate the wastewater into two end products: the treated water, which is clean enough to be reused, reducing the consumption of fresh water, and the solids fraction, which can either be recycled back to the process, sold as a product, or disposed of, depending on what type of solid it is and its quality. Zero liquid discharge technology will help to achieve the reuse and recycle of both water and valuable chemicals already at the source at the production facility, which is very important in realizing a profitable circular economy. Traditionally, most zero liquid discharge projects were driven by legislation only to meet all the regulations. But today we see an emerging trend that ZLD is also implemented based on pure process economics and for reducing risks and dependency. Becoming more self-sufficient, for example, by recovering valuable chemicals and utilizing at least the energy value from waste streams rather than just disposing them off, reduces the potential impact of factors outside your own control. And this will also contribute to reaching ambitious sustainability goals set for the business. Now we'll focus more on the technical aspects of the zero liquid discharge process, starting with a brief overview and then digging deeper into the thermal evaporation process. The overall ZLD plant will typically be a combination of many different technologies and process steps, and the most common ones are shown here, together with some numbers for a generic case treating 100 cubic meters per hour of oily wastewater with 1% salts, just to show what is happening in the different process steps. In the pre-treatment section, certain components which could generate fouling of the membranes in the downstream pre-concentration step, such as oils and calcium sulfate, are removed. Typical processes used in the pre-treatment section are chemical softening, flocculation, and solids removing using filters and other separators. The pre-concentration of the wastewater is often done with membranes, typically ultrafiltration and reverse osmosis. In many cases, the membranes are more attractive from a CAPEX and OPEX perspective than thermal evaporation, and the membranes can typically concentrate the stream up to 3 to 10 weight% solids, depending on the specific case. The limitation is normally the osmotic pressure and also the reliability of the membranes, and further concentration to reach crystallization will require thermal evaporation of the water. But in many cases, it's possible to remove the vast majority of the wastewater already here in the pre-concentration step, and the generic numbers shown here show an 85% volume reduction or water recovery already using the membranes. In the Following thermal evaporation process, the remaining water is evaporated and the solids in the wastewater starts to precipitate or crystallize. These crystals are then separated from the liquid fraction using either mechanical separation processes such as filter presses or decanter centrifuges, or by thermal drying, for example in agitated thin film dryers or spray dryers. The wastewater may also contain some volatile components such as methanol or ammonia, and these will easily co-evaporate with the water and will end up as contaminants in the condensate stream or the purified water. Depending on the actual requirements in the recovered water, it might be necessary to also include a condensate polishing step to remove those contaminants. The working principle of the thermal evaporation system is removal of water by boiling, and this can be used for concentrating on many different fluids containing both dissolved and suspended solids, but also for concentration of high boiling liquids. It should also be mentioned that in many cases where it's not necessary, and in some cases it's not even possible to reach the full zero liquid discharge with a dry solids product, there the evaporation process can still be used for volume reduction, minimizing the amount of waste that needs to be disposed of, and also recovering most of the water. And there are several different evaporation technologies and configurations available in the market, both based on traditional shell and tube technology and based on gasketed plate and frame evaporators. In some evaporators, the vaporization process, that is the boiling, happens at the heat transfer surface, which is okay for clean applications. For the more demanding duties, for example, if there is high viscosity or high scaling potential, which is the case for most wastewater application and crystallizers, the so-called forced circulation and flashing evaporators should be used instead. Here, instead of having liquid boiling at the evaporator heat transfer surface, a pump is used to recirculate a large flow of liquid through the evaporator, and the liquid is heated just a few degrees. But due to the higher pressure from the pump, boiling is suppressed on the heating surface, and the heated liquid is then flashed into the separation vessel, which is operating at lower pressure, where the evaporation and concentration then happens. This forced circulation evaporator is the safest choice for wastewater and CLD applications, and the main reasons I will explain in the next few slides. When selecting your evaporator technology, it's also important to choose the optimal system based on availability and cost of different energy sources. The evaporation process, boiling of water, needs an energy source to drive the process, and that can be either a thermal energy source, such as steam or hot water, or it can be electricity, each offering different advantages. In the mechanical vapor recompression or MVR system, using only electricity to drive the evaporation process, the water vapor that has boiled off from the product in the evaporator is compressed in a mechanical compressor or fan and can then be used as the heating media for the evaporating process. The MVR system is very energy efficient, normally resulting in lower operating costs as compared to the other alternatives. And it may also be easier to integrate into existing process plants since needing less utilities than other configurations. You could say being more of a plug-and-play solution. But the investment cost is normally slightly higher due to the cost for the compressor or fan. When utilizing steam or other thermal source, such as hot water for driving the evaporation process, the most common solution for increased energy efficiency is what is called multiple effect system, using several evaporator modules or effects in series, where the vapors from one effect are used to heat the next effect. This will reduce the steam consumption, and the more effects, the higher the steam saving, but of course at the expense of increased investment cost. Typically, the steam consumption for evaporating 1 ton of water is 1.1 to 1.2 tons steam in a single effect system. And when using multiple effects, this number can be divided by the number of effects to reach the actual steam consumption. In case higher pressure steam is available, a thermal vapor recompression system or TVR can be used to further reduce the steam consumption. Here, the higher pressure of the motive steam is used to compress and recycle part of the vapors produced in the first evaporator to the heating side of this evaporator. Together with selection of evaporator technology and configuration based on energy cost, there are also some other important factors to be considered to reach a reliable and robust CLD system with long lifetime and high availability. The most important factors are fouling, corrosion, and then we have something called we call general uncertainties when it comes to wastewater projects. And these different issues will be highlighted in the coming slides. The number one risk factor to be considered for wastewater evaporation and CLD is fouling or scaling. This is the unwanted accumulation of solids on evaporator heating surfaces that can have a significant impact on evaporator performance. The types, amounts, and build-up rate of fouling and scaling is determined by a combination of water chemistry and operating conditions, such as boiling temperature, possibility to get stagnant zones, and risk of dry spots. Using the forced circulation and flashing evaporator configuration, where we only heat the liquid, preferably with high circulation flow rate and a corrugated heat transfer area, will secure good wetting and turbulence across the full heat transfer surface, minimizing the risk of dry spots and stagnant zones. Here, the plate and frame evaporators have benefit over traditional shell and tube technology, providing the higher turbulence and shear forces, which will even enable a self-cleaning effect. The rapid movement and rotation of the liquid when flowing across the corrugated plates will minimize the buildup of fouling, and it can also tear off fouling that has already formed. The high shear forces also prevent smaller particles like crystals from precipitated solids from aggregating and becoming too large, which allows the plate and frame evaporators also to be used for crystallizing duties. The lower solids accumulation or fouling on the heat exchanger surfaces, the longer the runtime between cleaning cycles will be, and this will give a higher availability of the system and also help to reduce the total consumption of cleaning chemicals. During the cleaning cycle, which is typically by circulating a chemical cleaning agent inside the system using the recirculation pump, the higher turbulence and shear forces on the heat transfer surface will also be helpful, and the plate and frame heat exchangers can, in addition to this, also easily be opened up for inspection after finalized cleaning and, if necessary, be cleaned mechanically. Another risk typically involved in wastewater and CLD applications is corrosion. Corrosion can lead to failures that require long periods of downtime for costly equipment repairs or even replacement, and the corrosion risk is usually assessed based on the chloride content, pH value, and temperature. Chlorides can create devastating corrosive effects on many materials, especially at high temperatures and low pH. And chloride crevice corrosion is one of the most common reasons why heat exchangers, pipework, and vessels fail in CLD applications. It is very important to select proper materials as well as operating temperatures to achieve a long plant lifetime. One of the best materials to be used for chloride-containing fluids is titanium. The corrosion resistance of titanium can be 10 to 20 times greater than that of corrosion-resistant stainless alloys such as duplex or super duplex, making titanium an ideal material for CLD applications, at least for the heat transfer surfaces where the temperatures are the highest. The plate and frame heat exchangers with the higher thermal efficiency as compared to shell and tube technology provide an affordable choice for using titanium instead of duplex or super duplex, which may, as we'll see later, corrode within a very short time, while the lifetime of the titanium plates will be 10 years or more for this kind of service. And then the final, or this uncertainty risk, which comes from it's not always known to 100% what is the composition and other physical properties of the wastewater to be treated. Typically, the wastewater stream is a mixture of several sources, which may result in variations in flow rate and composition over time, and there might be modifications in the upstream production process, such as new process steps added or old removed during the lifetime of the CLD plant. All these factors can be considered as uncertainties for the design and functionality of the CLD system. What will be the actual amount and composition of wastewater to be treated now and tomorrow? Of course, we will use all means to get the best possible design basis for the process, such as computer modeling based on water chemistry, bench scale tests to determine important physical properties, but still it is very beneficial to use technology which is adaptable and robust for the CLD system. The plate and frame technology provides such adaptability and flexibility, since the heat exchangers can easily be modified after installation by adding or removing or replacing plates to achieve similar performance and fouling resistance for a new set of operating conditions. This type of modification is not possible with shell and tube heat exchangers without replacing the entire heat exchanger. To also have flexibility in the solids dewatering process, a decanter centrifuge can be used. The decanter centrifuge can remove particles within a large size span and also take variations in solids load over time. It is an electrically driven centrifugal separator with an horizontally installed bowl and conveyor rotating at very high speed to generate about 3000 Gs, which will efficiently remove also the very fine particles contained in the liquid, resulting in a more efficient CLD process, and the solids product leaving the decanter is almost dry. To give an overview of the full CLD evaporation system as designed and supplied by Alfa Laval, this picture shows the major components and flows for such a system. The feed, same properties as previously shown for the generic case, is mixed with a large flow of fluid from the separator vessel. The recirculation pump, installed at the bottom, sends this mixture through the gasketed plate and frame evaporator using the corrugated plates in titanium material for forced circulation and flashing evaporation. The plate corrugation gives the high turbulence and shear forces, helping to reduce fouling and scaling, and the titanium material will help to prevent corrosion. The flow rate of recirculated liquid is selected to avoid dry spots, stagnant zones in the heat exchanger, and the pressure created by the pump will help to avoid boiling of the liquid at the heat transfer surface. The heated liquid then passes through a flashing orifice, reducing the pressure and allowing part of the water to evaporate, concentrating the liquid stream. And in a crystallizing system, the total solids content of the liquid being recirculated is typically around 40 weight%. 25 to 30 weight% is dissolved solids, and 10 to 15 weight% is suspended solids or crystals. Part of this stream is fed to the decanter centrifuge, where most of the crystals are removed by the forced gravitational separation. And as mentioned, the decanter centrifuge operates at high rotational speed, resulting in very high G forces, removing also the very fine particles and giving an almost dry solids fraction. And the remaining liquid phase from the decanter, the centrate stream, is more or less a saturated brine, which is recycled back to the evaporator for further evaporation of the water and crystallization of the salts. Just to show how real plate and frame wastewater evaporation systems using the forced circulation and flashing configuration can look like, here are two examples for two different applications and capacities. It may be possible to build very compact and modularized systems for smaller capacities, and for the larger systems, some prefabrication can be made to facilitate the installation. And as compared to the traditional falling film evaporators using the 10 to 50 meters long tube bundles installed in vertical position, a much more compact installation can be realized using the plate and frame concept. Finally, I will present a customer case which highlights the importance of selecting the correct materials and also confirms that plate and frame technology will work for crystallizing duties. This CLD plant is located in northern Spain, and the owner, a Spanish waste management company, experienced repeated issues with corrosion of a duplex stainless steel shell and tube heat exchanger. The unit, which was supplied by another manufacturer, was operating as the second effect in a two-effect evaporation system intended to provide zero liquid discharge of mixed oily wastewater. The process designer and system integrator originally selected shell and tube technology for this position since skeptic to using plate and frame technology, afraid that the crystals should plug the channels. And in order to still be affordable, this large piece of equipment, it was manufactured in duplex stainless steel. However, after only 3 months of operation, the corrosion issues were severe, and it was clear that higher grade material had to be used. But building this shell and tube using titanium tube bundle would be extremely expensive and delivery time would be very long. And therefore, the system integrator recommended replacing it with an Alfa Laval Alpha Flash plate evaporator using titanium plates. And to tackle the concerns of using plate and frame evaporators for crystallization, an Alpha Flash system with wider gap between the plates was selected. And this evaporator has achieved zero liquid discharge for more than 10 years without corrosion issues or major fouling and continues to perform. And a more compact installation, the adaptability and the full access to the heat transfer area are other valuable benefits received more or less for free by our Spanish customer as part of this replacement. That was the end of the presentation part, and I hope that we have been able to share some knowledge and thoughts about CLD that will inspire you to new applications and projects using this kind of technology. And in case of any questions, I will be happy to try to answer, and thank you all for listening.
Thank you, Christian. I have received loads of questions. One question was, is there a maximum total suspended solids in the feed to the evaporator?
Very good question. I mean, as mentioned, we can operate the plate and frame evaporator for crystallizing duty, and then we have somewhere between 10 and 15% weight suspended solids in the liquid being recirculated in the system. So a feed containing less than 10-15% weight suspended solids should not be any problem.
Good. Good question. We had also another question. When you make cleaning, how often do you need to make a cleaning in place, a CIP?
That will actually depend from application to application, and it's impossible to give a very straight answer on that. I mean, in some applications, you need to do CIP once per week, in some applications once per year, all depending on which are the components or the chemical composition of the water and temperature and so on. So it's not easy to give a straight answer. It has to be evaluated from case to case.
Okay, then we had a different question. In this plate heat exchanger, there are channel gaps. Is there a risk of plugging of these channels with crystals?
It is correct that there is a gap between the plates, and typically that will be 4 or 5 millimeters for those crystallizers that we design. And the particle size, the crystal size for these applications will be maybe 0.1 millimeter. So there is enough space for the crystals to move freely inside the channel. So that is not a problem.
Thank you. We had a new question on the topic of CIP. For solutions where you have a certain hardness which could cause a scale. What type of CIP chemicals are typically used?
Well, to remove hard scale or salt scale, we typically use acids. Some sort of weak acid that can dilute or remove or dissolve the scaling, but not, of course, harm the plates.
Okay. More questions on the similar topic. Is there any need for any continuous dosing of anti-scaling chemicals?
Typically, we will not use continuous dosing of anti-scaling agents. Instead, we adapt the process conditions like the recirculation flow to generate even higher turbulence and shear forces on the heat transfer area if needed, which will help avoiding to get scaling and fouling.
Okay. Let me see here. Can you expand a bit more about the typical maintenance for a system like this? How often is it needed to maintain the system? And what are the typical steps you make in a maintenance?
I would say that it's mainly the rotating equipment that will need regular maintenance, like the pumps and also the decanter centrifuge. I mean, changing gaskets and bearings from time to time. If we talk about the plate heat exchanger, as mentioned, the lifetime of the titanium plates is expected to be very long, 10 years or even more. And since the wastewater evaporation process is typically operated at fairly low temperatures, maybe 80 degrees at the highest, the lifetime of the gaskets will also be very long, 5 or 10 years, depending on which application it is. So I would say it's mainly the rotating equipment, and then it's just like normal pumps and other things that you should do that at certain intervals.
Mm-hmm. Thank you. We had another specific question. If acid wastewater were containing divalent ions with pH in the range of 1 to 2, if that can be treated with a configuration like this?
Depends on which ions it is, because if it's, when you mention divalent ions, if it's calcium and magnesium, then it's not a problem. But of course, if there's a lot of chlorides, then we need to select very low temperatures to avoid corrosion, also for titanium. But it's possible to do that by selecting the appropriate operating conditions, yes.
Good. Could you expand a bit more on when to select an electrically driven system such as an MVR and steam or hot water driven system like a multi-effect or TBR?
I would say that the major factor to be considered is what utilities do you have available at site. I mean, if you already have steam available or some other thermal source like hot water, and it's more or less, it's not too costly, then the multi-effect system will be fairly attractive since it has a lower investment cost. But if you don't have steam, or if steam is fairly expensive, then it may be more, I mean, in the long run, more economical to use the MVR system. And as mentioned, the MVR system only uses or mainly uses electrical power to drive the evaporation system and needs less cooling water, for example. So there are some other benefits using that, and it's more of a plug and play type of evaporator. So in principle, you could say, depending on which utilities you have at site and what is the cost for the different utilities you have.
Thank you. Last question here. Can we apply zero liquid discharge for tannery industries? Which treating methods would you suggest?
No, I'm not 100% sure what is tannery industry.
I think it's textile.
Okay, then I would say that yes, it's possible. If it's salts to be removed, then it's just a normal evaporator. And I mean, if it's salts, you can actually go for zero liquid discharge. You actually precipitate or crystallize the salts to get them out. In some other cases, it could be, for example, dyeing chemicals, which can be concentrated and maybe reused in the process. But I'm pretty sure we can find a solution for that application as well.
Thank you, Christian. A lot of good questions received, and we are very thankful for you joining this webinar. It has been very interesting questions we have received, and we are thankful for your participation. And if you have any further questions, please do not hesitate to contact us. You can reach us. Simplest perhaps is via our web page, which you can see on the screen. There is a contact formula to reach us. Again, thanks a lot for participating, and wish you a nice continued day. Thank you.
Thank you very much.